this data set consists of 10 examples, all from x1, y1, x2, y2, all the way to x10, y10. And this is a very simple data set to understand. We have a variable x that represents, let's say, square footage of a house, and y that represents, let's say, the price of a house. And we are asked to predict the price of a house for a house that we have never seen before. And in this case, since the only feature available to us is square footage, which is on the x-axis, this is the house that we have never seen before, let's say. So we're given all of these data points, but this one we're not given, no one is giving this. So we are going to be predicting the price of the house for that data point. Okay, so where about the y will actually be? That is really the problem. And as we said earlier in another video, we will call these predictions y-hats. And according to the Vapnik block diagram, the block diagram we have seen in the earlier video, the first thing that we have to do is to decide on the hypothesis set. And I'm actually going to start, everyone is entitled to a valid hypothesis. I'm going to start with a valid hypothesis. Let's assume that I believe that the function f is that underlying this data set is this straight line. So I'm going to be calling this function g0, and I'm going to further qualify it as g0 of x comma w is w0, and every hypothesis is, of course, is able to give us a prediction y hat. So this is basically the equation of my first hypothesis. Is it a valid hypothesis? Yes, it is. For many of you, it probably will be you're now thinking that this is actually a too simple hypothesis, but just to remind you that the computer is not able to plot. The computer is actually pretty stupid. It will actually, we need to teach the computer how to come up with a good enough hypothesis for our problem. And so for now, as far as the computer is concerned, G0 is as good as any hypothesis. All right, so that is one hypothesis. Let's now move on into yet another hypothesis. Let's plot another hypothesis. Let's plot the hypothesis, maybe this one. Someone says that that's another valid hypothesis. I'll call this one, to distinguish from the other one, G1. So the according to this G1, we will be making predictions y hats. This G1 is that it can now be written as W0 plus W1x. And I hope you remember the equation of a straight line, mx plus b, is exactly the same equation. Now we are not really constraining the hypothesis to be parallel to the x-axis, but we have introduced another parameter, w1, and we started using actually the features that someone is giving us to draw that hypothesis, to define this hypothesis. So the hypothesis that we have up to now, I hope you realize that these are an infinite, we can generate an infinite set of lines. Even just staying a little bit only in the first hypothesis, like let's say the first one we have defined, by varying W0, which is the only knob that someone is actually giving us, we can actually plot an infinite number of parallel lines to the x-axis. And this is the reason why I actually call this W0 parameters, because we are actually going to be able to vary them and vary them intelligently later on. In the same way, by varying W0 and W1 at the same time, we are able to draw any straight line parallel to the x-axis, not parallel to the x-axis, with any intercept and any slope. All right, so now what we can do is we can continue, and let's see that someone suggests another hypothesis. And the other hypothesis is as follows: W0 plus W1x plus W2x squared. Now, you're going to say, hold on a second, what is really this term over here? Let me just draw it and then kind of explain it. Maybe the other hypothesis will look like this. G2, let me call it. And in this case, hypothesis, we have actually started introducing effectively new features. The only thing that someone gave to us in our data set is x, but over here we see some function of x, let's say x squared or x by x, and we are going to suggest that this hypothesis is also valid, and with this hypothesis we are definitely expecting these equations to draw quadratic lines. It's a quadratic function, so something like that could potentially be drawn for specific values of W0, W1, and W2. In fact, we can actually draw an infinite set of lines, which are now going to be more complicated than just a straight line. And we can actually continue all the way to y hat, let's say, let me call this G9 of x comma W. And here I'm going to have a very interesting hypothesis. In this hypothesis, we will, let me draw it. It could be a hypothesis that goes through all of the points that someone gave me. I drew it approximately, obviously. And this hypothesis is the point where we actually stop, and I think we drew enough of them. And now we actually need to move now to the discussion on how are we going to evaluate them. Some of you may already have plotted in your minds the sinusoidal-like hypothesis, which is the final hypothesis. But mind you that this line, which is actually also shown in the notes, you just forget it, because this green line in your notes is the target function, and the machine has absolutely no information about this target function other than the fact that it exists. Before we understand exactly how we are going to go about designing this loss function, it's our responsibility, by the way, to design the loss function, and we will need to just do some kind of thinking here. Ultimately, as we mentioned, we need to design a predictor that will actually produce good results, good prediction results. Now we need to understand what this good means, but for x's that we have never seen before. So let's pick one x over here. This x, this is, I will call this the so-called x nu. And I just want to make you understand exactly how predictions will be done. So for that x nu, I have various hypotheses. Well, for hypothesis G0, I will look up this x nu. I'll put this inside that kind of function G0. And given the W0, which I have right now drawn, I will look up the y hat. Well, the y hat is exactly at the same place as where the W0. That's my y hat for the sort of zeroth hypothesis. That is, let's say, for the y hat for the G1 hypothesis is approximately over here. This is another y hat. All right, and how about the G2? Well, you probably guessed it, is right here. That's my y hat. And as far as the G9 is concerned, is actually over here. It is far away from everything else. I hope it's not a too busy kind of diagram. You can actually see exactly what I have done over here. All right, so every G parametric functions give us the opportunity to do as many predictions as we want. And now that we have seen exactly how we'll do predictions, I think it's worthwhile mentioning that what is really our intuition as far as the good predictor is. A good intuitive way of thinking about the loss function is the following. Since someone gives us some examples, maybe we can just use those examples that evidently have a label to gauge how close to the existing data our predictions are. If they are close enough, then that function should return some scalar back to us. And if they are far away, that scalar should actually be larger than the previous case when they were close. So that's the intuitive way of understanding loss functions, how they will behave. So let's see now what is a good way of sort of providing this mathematically. What we describe with words, now we'll put down this thing in a math equation that defines this kind of loss function. Definitely we expect this loss function that I will symbolize with L, the calligraphic L, to be a function of two things. The first one is, on one hand, our predictions, the y hats, and on the other will be the ground truths or our labels y. And as we kind of just described, we expect to see over here some form of distance between, let's say, our prediction y hat for the specific example that we have, the ith example, and some form of distance between that prediction and the ground truth. So as we discussed, if that difference is large, then that kind of a loss function should return a large number. And if that difference is small, a small number, that kind of goes, is compatible with what we had just discussed. However, in some instances, for some specific examples, the prediction is a larger number than the ground truth, and or vice versa. We want to, at the end of the day, have a number which is kind of positive, irrespectively of how the prediction is larger or lesser than the ground truth. So what we will do is we will square them, and we will square to convert them into positive numbers. So we have now a difference for every single example that we care for. So, however, we do not know exactly what to do with, let's say, m numbers. What is information that conveys to us? Probably it would be much better if we are to get just a single number out of these differences. And in this case, it's very easy to convert m differences to a single number. We're just going to sum over all of our examples and normalize by the number of examples we are given. And this is really the loss function that we are going to use from now on. It made intuitive sense to us. This function is in fact known as mean squared error, or MSE, and it is a standard function for regression problems. Later on we will see that this function that right now was presented from a kind of intuitive perspective, in fact it is derived out of a concept that we'll actually call a cross-entropy loss function. So all of these will actually come a bit later, but for now I hope this discussion was understood. And so this is these loss functions, just like any loss function for us, will return back, as you understand, a single scalar number. If that number is large, we are not going to be doing very well, because this means that we are far away from our predictions. If that number is very small, we are doing much better. Okay, so something else that I wanted to mention also, I should also highlight the fact that behind the y hat is the parameter w. So behind the y hat there is a hypothesis, and therefore sometimes you actually see this being written as L of w, and this is exactly identical concepts and identical notations. In many instances we do want to write it like this, because we want to emphasize the fact that by changing these w parameters, we are actually going to be changing the observed loss.